Welcome back to Scientia Academiae. Today, we're diving into some intriguing math problems from the May-June 2015 O-Level exams. Let's get started. And remember, no calculators allowed. Question 1. In part A, we need to evaluate 3 divided by 8 plus 1 whole 1 divided by 3. First, let's convert the mixed number 1 whole 1 divided by 3 into an improper fraction. To do this, we multiply the whole number, 1, by the denominator, 3, and then add the numerator, 1. So, 1 times 3 plus 1 is equal to 4, giving us 4 divided by 3. Now we have 3 divided by 8 plus 4 divided by 3. To add these fractions, we need a common denominator. The least common multiple of 8 and 3 is 24. Now, we convert 3 divided by 8 to have a denominator of 24. 3 over 8 multiply by 3 over 3, which is equal to 9 over 24. Next, we convert 4 over 3. 4 over 3 multiply it by 8 over 8, which is equal to 32 over 24. Now we can add the two fractions. 9 over 24 plus 32 over 24 is equal to 41 over 24. Finally, we can express 41 over 24 as a mixed number, 1 whole 17 over 24. Now, moving on to part B, we need to evaluate 5 minus 3 bracket open 2 minus 1.4 bracket close. First, we simplify the expression inside the brackets. 2 minus 1.4 is equal to 0.6. Now our expression looks like this. 5 minus 3 bracket open 0.6 bracket close. Next, we multiply 3 by 0.6. 3 times 0.6 is equal to 1.8. Now our expression is 5 minus 1.8. Finally, we perform the subtraction. 5 minus 1.8 is equal to 3.2. Question 2. In part A, we need to evaluate the expression 1.3 plus 2.9 over 0.2. Let's start by adding the numbers in the numerator. First, we add 1.3 and 2.9. When we do this, we find that 1.3 plus 2.9 equals 4.2. Now our expression looks like this, 4.2 divided by 0.2. To perform this division, let's convert 4.2 and 0.2 into whole numbers. This can be done by multiplying both of them with 10, which gives us 42 divided by 2. Now let's simplify. 42 divided by 2 gives us 21, which is the final answer. Now, let's move on to part B, where we evaluate 2 whole 1/4 multiplied by 1/5. First, we need to convert the mixed number, 2 whole 1/4, into an improper fraction. To do this, we multiply the whole number, 2, by the denominator, 4, which gives us 8. Then we add the numerator, 1, so we have 8 plus 1, which equals 9. This gives us 9 over 4. Now, our expression looks like this, 9 over 4 multiplied by 1 over 5. To multiply these fractions, we simply multiply the numerators together and the denominators together. 9 times 1 equals 9, and 4 times 5 equals 20. So we have 9 over 20. This fraction is already in its simplest form. Question 3. In part A, we have a diagram where 6 small triangles are already shaded, as shown. The task is to shade one more small triangle so that the diagram will then have one line of symmetry. To solve this, we first need to identify a potential line of symmetry. A line of symmetry divides the diagram into two identical halves. Since there are 6 triangles shaded, we can look for a triangle that, when shaded, will create a mirror effect across this line. By shading one additional triangle that is directly opposite to an already shaded triangle, we will achieve that symmetry. After shading this additional triangle as shown in diagram, we now have a total of 7 shaded triangles arranged in such a way that each side of the line of symmetry mirrors the other. The diagram shown in part B has rotational symmetry. We need to mark the center of rotational symmetry with a dot, and write down the order of rotational symmetry. First, let's find and mark the center of rotational symmetry. To do this, we observe the shape carefully. The center of rotational symmetry is the point around which the entire shape can be rotated and still look the same at certain intervals. In this diagram, the center is located at the middle hexagon, which is surrounded by other identical hexagons. We mark that center with a dot. Now that we've identified the center, let's determine the order of rotational symmetry. This refers to the number of times the shape fits perfectly into its original position during a full rotation of 360 degrees. As we rotate the shape, we can see that it aligns with its original outline 3 times in one complete turn. Therefore, the order of rotational symmetry for this shape is 3. Question 4. In this question we're going to order some numbers from smallest to largest. We have the following values: 13 over 20, 0.7, 7 over 12, 0.64, and 5 over 8. Are you ready? Let's dive in. First, we'll convert each fraction to a decimal to make comparison easier. Let's start with 13 over 20. To convert it, divide 13 by 20. 13 divided by 20 equals 0.65. Next, let's convert 7 over 12. Dividing 7 by 12 gives us approximately 0.58. Now, let's convert 5 over 8. Dividing 5 by 8 results in 0.62. Finally, we already have 0.7 and 0.64. Now, let's list them in order from smallest to largest. So, our ordered list is 7 over 12, 5 over 8, 0.64, 13 over 20 and 0.7. Question 5. In part A, express 3 whole 3 divided by 4% as a fraction in its simplest form. To convert this mixed number into a fraction, we start with multiplying 4 into 3 and then adding 3, making 15 over 4. That is an improper fraction. Now, we have 15 over 4%. To convert 15 over 4% to a fraction, we divide 15 over 4 by 100. This is the same as multiplying by 1 over 100, which gives us 15 over 4 times 1 over 100 equals 15 over 400. Now, we need to simplify 15 over 400. Both the numerator and denominator can be divided by 5. Dividing 15 by 5 gives us 3, and dividing 400 by 5 gives us 80. So, 15 over 400 simplifies to 3 over 80. Therefore, 3 whole 3 divided by 4% expressed as a fraction in its simplest form is 3 over 80. In part B, we're going to arrange some fractions in order from smallest to largest. The fractions we have are 4/5, 3/4, and 31/40. To compare these fractions easily, it helps to express them in decimals. Starting with 4/5. When we divide 4 with 5 we get 0.8. Next, let's convert 3/4. To convert, divide 3 by 4, which gives us 0.75. 31 divided by 40 gives us 0.77. Now, let's arrange them from smallest to largest. First is 3/4. Next is 31/40. Finally, 4/5. Question 6. In this question we're tackling a geometry problem involving a trapezium. We know the area is 120 square centimeters, the height is 12 centimeters, and we have some relationships between the lengths. Are you ready to solve for B? Let's get started. First, let's recall the formula for the area of a trapezium. Area equals 1/2 times the height times the sum of the lengths of the two parallel sides. In our case, we have the height is 12 centimeters. One base A is equal to B. The other base B is equal to 4 times B, which we can express as 4B. Now we can plug these values into the area formula. So, we set up the equation. 120 equals 1/2 times 12 times the sum of B and 4B. Let's simplify that equation step by step. First, 1/2 times 12 is 6. So our equation becomes 120 equals 6 times the sum of B and 4B, which is 5B. Next, we can simplify that. This gives us 120 equals 30B. Now, to find B, we need to divide both sides of the equation by 30. So we have b equals 120 divided by 30. Now, let's do the division. 120 divided by 30 is 4. So, b equals 4. Therefore, the value of b is 4 centimeters. Question 7. Part A involves finding the difference between two numbers, the square root of 10 and 3 whole 1/6. This means we will subtract the square root of 10 from 3 whole 1/6. 3.166667 minus 3.162278 equals. Let's do that step by step. First, align the numbers for subtraction. 3.166667 minus 3.162278. Now, subtract each digit starting from the right. When we perform the subtraction, we find that the difference is approximately 0.004389. Now, we need to express our answer in two significant figures. The first two significant figures in our difference are 0.00, since we start counting from the first non-zero digit. However, since we're interested in the actual value, we can see that the first non-zero digits we encounter are 0.004, which gives us the significant figures. Thus, our answer rounded to two significant figures is 0.0044. So, to summarize, the difference between 3 whole 1/6 and the square root of 10 is approximately 0.0044, expressed in two significant figures. In part B, we're tackling an estimation problem that involves calculating the sum of the squares of two numbers and then finding the square root of that sum. Let's dive right in. We're given two numbers, the square root of 2.986 squared and 4.002 squared. Our goal is to estimate the value of this expression and then round it to the nearest whole number. First, let's break this down step by step. We'll start with the first part, estimating the square of 2.986. Now, 2.986 is very close to 3. For our estimation, we can round it to 3, since it simplifies our calculations. When we square 3, we get 3 multiplied by 3, which equals 9. Next, let's move on to the second number, 4.002. This number is very close to 4, so we can round it to 4 as well. Squaring 4 gives us 4 multiplied by 4, which equals 16. Now we have both squared values. The estimated square of 2.986 is approximately 9. The estimated square of 4.002 is approximately 16. Now, let's add these two results together. 9 plus 16 equals 25. Next, we need to find the square root of this sum. The square root of 25 is the number that, when multiplied by itself, gives us 25. That number is 5. Finally, we round this result to the nearest whole number. Since 5 is already a whole number, we can conclude that the estimated value of the expression is 5. To summarize, we estimated the value of the square root of 2.986 squared plus 4.002 squared to be 5 when rounded to the nearest whole number. Question 8. In this question we have an interesting probability problem to solve involving colored counters in a bag. Let's break it down step by step to find out how many yellow counters are in the bag. We know that the bag contains a total of 60 counters, which include red, blue, and yellow counters. We also have some information about the probabilities of selecting each color. First, let's look at the probability of selecting a red counter, which is 2/5. This means that if we were to randomly select a counter from the bag, 2 out of every 5 selections would be red. To find out how many red counters are in the bag, we can use this probability. Since there are 60 counters in total, we multiply the total number of counters by the probability of selecting a red counter. So, we take 60 and multiply it by 2/5. To do this without a calculator, let's break it down. First, we divide 60 by 5, which gives us 12. Then, we multiply that result by 2, which gives us 24. So, there are 24 red counters in the bag. Next, let's examine the probability of selecting a blue counter, which is 5/12. Similarly, We can find out how many blue counters are in the bag by multiplying the total number of counters by this probability. So, we take 60 and multiply it by 5/12. First, we divide 60 by 12, which gives us 5. Then, we multiply that result by 5, which equals 25. Thus, there are 25 blue counters in the bag. Now, we've found the number of red counters and blue counters. We can add these two amounts together. 24 red counters plus 25 blue counters equals 49 counters. Since we know that the total number of counters in the bag is 60, we can find the number of yellow counters by subtracting the combined total of red and blue counters from the total number of counters. So, we take 60 and subtract 49. 60 minus 49 equals 11. Therefore, there are 11 yellow counters in the bag. To recap, we determined that there are 24 red counters, 25 blue counters, and 11 yellow counters in the bag. Question 9. This question involves scientific notation and standard form. We will be working with two values, p, which is 4 times 10 raised to the power of 5, and q, which is 7 times 10 raised to the power of 6. Let's break this down step by step and find both p squared and the sum of p and q. First, we need to calculate p squared. We know that p is 4 times 10 raised to the power of 5. When we square a number in scientific notation, we square both the coefficient and the base while adding the exponents. So, let's square p. First, square the coefficient, which is 4. 4 squared equals 16. Next, we square the base 10 raised to the power of 5. When we square 10 raised to the power of 5, we multiply the exponent by 2. 5 times 2 equals 10. Putting this together, we have p squared equals 16 times 10 raised to the power of 10. Now, we want to express this in standard form. In standard form, the coefficient should be between 1 and 10. Since 16 is not in that range, we can convert it. 16 can be written as 1.6 times 10 raised to the power of 1. So, we can rewrite our expression. P squared becomes 1.6 times 10 raised to the power of 1, multiplied by 10 raised to the power of 10. When we multiply the powers of 10, we add the exponents. 1 plus 10 equals 11. Thus, p squared in standard form is 1.6 times 10 raised to the power of 11. Now, let's move on to part B and find p plus q. We have p equals 4 times 10 raised to the power of 5. Q equals 7 times 10 raised to the power of 6. To add these two values, we need them to have the same exponent. Since the exponent in q is greater, let's convert p to have the same exponent as q. We can rewrite p. 4 times 10 raised to the power of 5 can be expressed as 4 times 10 raised to the power of 5, which is the same as 4 times 0.1 times 10 raised to the power of 6. Now, 4 times 0.1 equals 0.4. So we can write p is now 0.4 times 10 raised to the power of 6. Now we can add p and q. P plus q equals 0.4 times 10 raised to the power of 6 plus 7 times 10 raised to the power of 6. Since both terms now have the same exponent, we can combine the coefficients. 0.4 plus 7 equals 7.4. So, we have p plus q equals 7.4 times 10 raised to the power of 6. Both results are now in standard form. For part A, p squared is 1.6 times 10 raised to the power of 11. For part B, p plus q is 7.4 times 10 raised to the power of 6. Question 10. Fariza is traveling from London to Astana, but her journey involves a stopover in Moscow. Now, keep in mind that there is a time difference between London and Astana. Astana is 5 hours ahead. So, for example, when it's 10 o'clock in the morning in London, it's already 3 o'clock in the afternoon in Astana. Fariza's flight leaves London at 12:25 in the afternoon, and it takes 4 hours to reach Moscow. Once she arrives in Moscow, she has to wait for her connecting flight. Her layover lasts 4.5 hours. After waiting, she finally boards the flight to Astana and arrives there at 5:25 in the morning, local time in Astana. Now, the question asks, how long was Fariza's flight from Moscow to Astana? Let's break down this problem step by step so that we can easily find the answer without using a calculator. First, Fariza's journey begins in London. She takes a flight to Moscow, and her departure from London is at 12:25 in the afternoon. This flight takes a total of 4 hours. So, adding 4 hours to her departure time, Fariza lands in Moscow at 4:25 in the afternoon, according to London time. However, remember that Moscow is 3 hours ahead of London. This means, when it's 4:25 in London, it's actually 7:25 in the evening in Moscow. Now, once Fariza reaches Moscow, she has to wait for her next flight to Astana. Her layover in Moscow lasts for 4.5 hours. If we add 4.5 hours to the local time of 7:25 in the evening, her flight departs from Moscow at exactly 25 minutes before 9 in the evening, Moscow time. Next, Fariza's flight from Moscow to Astana takes off. She lands in Astana at 5:25 in the morning, according to Astana's local time. However, Astana is 1 hour ahead of Moscow, so we need to convert Astana time back to Moscow time. When it's 5:25 in Astana, it's actually 25 minutes after midnight in Moscow. So now, we know the departure time from Moscow was 25 minutes before 9 in the evening, and her arrival time, when converted to Moscow time, was 25 minutes after midnight. This means the duration of her flight from Moscow to Astana was 3.5 hours. To summarize, Fariza's flight from Moscow to Astana took 3 hours and 30 minutes. And that wraps up our math exploration for today. I hope you found these problems engaging and insightful. Don't forget to like, subscribe, and hit the bell icon for more educational content from Scientia Academiae. See you next time.